fourth installment of the Scuba Educator's Equipment Service course. Today we're going to be talking about regulator first stages. Without reliable regulators, scuba diving could not exist. The cylinder valve delivers high pressure gas to the first stage of the regulator. The regulator first stage has two main functions. Besides keeping high pressure gas from leaking, it delivers interstage pressure or IP gas, some call this low pressure or LP gas, to the regulator's second stage, and provides a reading on high pressure supply pressure through a gauge. Regulators reduce high pressure supply pressure to ambient pressure in two steps. The first stage reduces high pressure supply pressure, high pressure, to what is called interstage pressure, or IP, sometimes called intermediate pressure or low pressure. However, interstage pressure is a more accurate term. The scuba regulator is a demand regulator because it only delivers gas on demand when the diver takes a breath. It's also an open circuit regulator because the expired gas is released into the water. Closed circuit regulator systems allow a diver to rebreathe their own gas. These are found in rebreathers. The demand regulator for use in diving was actually invented in the mid-1860s, but it was not possible to get high pressure gas at that time. The same design from the 1860s was modified and perfected in 1943 by Émile Gagnon and Jacques Cousteau. Early regulators were single-stage regulators. Once the first stage has delivered interstage pressure gas pressure to the second stage is responsible for reducing the interstage pressure to ambient pressure so the diver can take a normal breath. First stage interstage pressure is determined by the manufacturer and is typically in the range of 135 to 165 pounds per square inch gauge at the surface. As the diver descends, ambient pressure goes up as a result of pressure related to the weight of water. Therefore, the first stage must increase interstage pressure to account for the pressure increase at pressures greater than 14.7 pounds per square inch absolute. As a result, the actual interstage pressure is the initial interstage pressure plus the additional ambient pressure in pounds per square inch gauge, PSIG, which you learn to calculate in your nitrox course. If your first stage has an interstage pressure of 145 PSIG at sea level, it will have an interstage pressure of 159.7 PSIG at 33 feet. In other words, 145 plus 14.7 PSIG. Interstage pressure is something the service technician checks and can adjust. It is easy to check. Get a small gauge that attaches to the BC inflator hose to eliminate either high or low interstage pressure as a potential problem when troubleshooting a regulator. High pressure starts at cylinder service pressure and decreases through the dive. Use your submersible pressure gauge, or SPG, to monitor gas pressure and gas supply. Everything going on in a regulator is as a result of opposing forces and pressure differentials. The engineers that design regulators use differences in pressure to make parts of the regulator move in a predictable way. There are two first stage designs, piston and diaphragm. Each of these are reliable and time-tested. Piston first stages can be balanced or unbalanced. Modern diaphragm first stages are all balanced. What does this mean? Well, balanced means that the performance of the first stage is unrelated to the high pressure supply pressure, except when the cylinder is nearly empty. In other words, the interstage pressure in a balanced first stage remains relatively stable no matter what the cylinder supply pressure is. Let's talk about first stage construction. The bodies of most first stages are made of machined brass plated with chrome. Some are made with machined titanium at about twice the price. At least one regulator first stage is made of 316 grade stainless steel. Scuba Pro makes a cast brass first stage, the Mark 21, which offers high performance at a lower cost. For a manufacturer, just say Atomic, the internal components of all the first stages of a particular model are the same or nearly the same, despite differences in the body metal. What do we mean by machining? Machining means that a part is manufactured from raw stock, typically a piece of square or round metal stock. In 2020, machining is done by using computer-controlled mills, grinders, and polishers, and this process is known as CNC, or computer numerical control. Visit YouTube to watch videos of regulators being manufactured. Yoke versus din. Most first stages in the United States use the yoke retainer system, which is okay up to 237 bar or 3,442 psig. DIN stands for Deutsche Institut für Normung, or the German National Standard. The German standard for high-pressure scuba regulators is a first stage that threads into the valve. The high-pressure O-ring is captured by the DIN design and is therefore a safer design for high pressure up to 4,350 psig or 300 bar cylinders. At that pressure, a yoke type retainer, it's possible that the O-ring could be forced out of position and leak. In the United States, where cylinder pressures do not exceed 3,442 psig, DIN is not necessary. However, some divers like to be different and use DIN first stages. Yoke-mounted regulators can also be fitted with a DIN retainer. Conversion from yoke to DIN is very simple as long as the technician is trained and has the correct tools. In some parts of the world, a diver may need or want to use a DIN-adapted first stage because of the high-pressure cylinders. The regulator for yoke and DIN is the same regulator and can handle 4,350 psig. And here's a picture of two models of regulators. On the left, a balanced piston regulator. On the right, a balanced diaphragm regulator. The top picture in each case shows a DIN retainer design, and the bottom pictures are yoke retainer. And in this diagram on the left, you can see the high pressure coming in through the filter into the first stage. That big red arrow on the top is the high pressure. and it passes through a small orifice that's machined into the body of the regulator. In some modern designs, that seat is actually removable and replaceable if it gets damaged, which is a good idea. The piston itself contains a soft seat which mates up and seals on the hard seat and stops gas flow. And on the right you can see the piston, the main spring, and in the end of the top end of the piston, the narrow end, is where the soft seat is retained. Water is allowed to enter the regulator body to provide ambient force so that the interstage pressure increases as the diver descends. So the first stage will actually automatically increase interstage pressure as ambient pressure goes up, i.e. the diver is descending, which makes it easy to breathe at any depth. In the unbalanced piston first stage, when the gas is turned on, high pressure gas flows into the first stage, comes out as interstage pressure, and flows down the regulator hose to the second stage where it stops. When that gas stops, if there are no leaks, the regulator will then go into lockup at some interstage pressure. Hopefully the interstage pressure will be the desired interstage pressure, the one that the engineers have designed the regulator to deliver. This happens very quickly, so you hear gas flowing through the hose and the regulator will not perceptibly leak and will just simply go into what's called lockup. So you have interstage pressure going down the hose, stopping at the second stage, and high pressure gas is still entering the first stage. When the diver takes a breath, the interstage pressure is lowered inside the regulator body, and this allows the piston and the soft seat to move away from the hard seat. When inhalation stops, the interstage pressure builds up again and closes off the soft seat. During the breathing cycle, air flows past the piston, so this is called a flow-by piston. Let's look at a diagram. So here's an example of the cutaway of the first stage unbalanced piston. When the diver has taken a breath, the interstage pressure is lowered, the piston moves away from the orifice, and gas flows down the interstage pressure hose to the second stage. Very simple. Stop breathing, the piston will close up against the orifice. Let's talk about balanced piston first stages. A balanced piston first stage allows gas pressure to flow to both ends of the piston and lets high pressure gas surround part of the piston shaft without allowing the high pressure gas pressure to create downstream force. The interstage pressure is stable no matter what the high pressure supply pressure is, and the performance of the first stage is therefore unaffected by high pressure and is predictable. Gas flows through the piston. We call this a flow-through piston, and very large gas flows are possible in balanced piston regulators. The Scuba Pro Mark 25, for example, can flow over 8,500 liters per minute. The unbalanced piston regulator, Mark II, flows about 3,000 liters per minute. So let's look at a balanced piston first stage in cutaway. And the one thing you'll notice immediately is that instead of the high pressure coming in to impact the small end of the piston directly, it comes in from the side. So high pressure is surrounding the small end of the piston, and it's kept from leaking down into the spring chamber by an O-ring, in some cases a series of O-rings. The high pressure soft seat is included in the top of the regulator in a little cap, and we'll talk about that when we get to the hands-on portion. Some of that high pressure gas flows straight across into the hose going to the submersible pressure gauge, so that would be our high pressure hose, and that's a high pressure port. The same forces are involved as in the unbalanced first stage. You have high pressure coming in, although now it's not creating downstream force because the gas is allowed to flow around the piston instead of pushing on the small end of it. The spring force and the ambient pressure force are the same. Those two forces will try to move the piston away from the soft seat and open it so that the gas can flow to the diver. In this case, though, the gas flows down the center of a hollow piston shaft and directly into ports at the bottom of the regulator that go out to the second stage, the interstage pressure ports. The same thing happens in the balanced regulator first stage as in the unbalanced. When the diver takes a breath, the interstage pressure is reduced, and the spring force and ambient pressure force cause the piston to move away from the orifice, from the soft seat rather, and the diver is able to get gas delivered to the interstage pressure hose. In the balanced piston design, the piston itself is a precision machined part and must be treated very carefully. The hard seat of the balanced piston is actually machined into the small end or narrow end of the piston stem, and so if you scratch or damage that at all, it's likely you're going to have a leak. So when we're working on these things, we tend to protect the end of that piston shaft very carefully. In this case, we've put a little piece of brass that's been precision machined to fit the hole so that we can't knock it over and damage the piston while we're working on it or cleaning it. All right, sidebar. Adiabatic temperature fluctuation. What do we mean by that? Simple. When gas is compressed, it gives off heat. So if a scuba cylinder has been just filled, put your hand on the side of it. It's going to be hot. When the gas expands, it absorbs heat. The principle of refrigeration. In the regulator first stage, it can get very warm when the high pressure gas flow comes into the first stage and stops during lockup, which is why oxygen percentage is limited in nitrox mixtures. We don't want heat and oxygen to combine with fuel and cause a fire. When the gas starts flowing, and if it free flows, the first stage may get very cold. So there's a wide range of temperature fluctuation going on in the first stage of the regulator. And we'll talk about this more when we get to the next lecture. Now let's talk about balanced diaphragm first stages. The diaphragm first stage is a different design with a lot more moving parts. In the diaphragm first stage, interstage pressure actually increases as the high pressure supply pressure drops. The balanced design allows the first stage performance to remain stable even as the high pressure supply pressure decreases. Diaphragm first stages have an internal hard seat and a soft seat that moves away from and back to the hard seat. In this diagram, we can see that the hard seat is machined into the body of the first stage, and the soft seat moves back and forth on a little seat carrier that's controlled by a spring. So it will tend to remain closed until it's moved. How do we move it? Good question. The same forces are involved. We have high pressure force coming into the regulator through the filter. And in this case, you can see that it's surrounding the seat carrier. So it's not providing downstream force, and that's important. So that means this is a balanced design. We also have spring force and ambient pressure force that's tending to push the soft seat away from the hard seat. If you look at the left cutaway, there's a little shaft coming off the end of the spring pad, and it rests on the diaphragm. When that diaphragm moves up, that little pin pushes the seat carrier away from the hard seat. So that's how it opens. So the ambient pressure and spring force is going to tend to push that soft seat away from the orifice or hard seat. The interstage pressure force is what keeps the system closed. It's going to work against ambient pressure and spring pressure to force the pin down and allow the little tiny spring that's backing up the seat carrier to close the soft seat against the hard seat. So piston versus diaphragm, does it matter? Both are reliable, high-performance designs. Advantages of the piston are a much simpler design, one moving part. Highly machined piston in the balanced piston regulator makes them very stable. They also have a lower service cost because of the number of parts that are involved in the first stage. And they can flow very, very high rates of gas, which is great for technical divers that dive deep where the gas density is very high. The disadvantages of a piston are the high flow rate can exacerbate ice formation because it causes low temperatures in the first stage and can cause the regulator to freeze up if the second stage starts to free flow. And you might be concerned about that if you're an ice diver, but I will tell you that modern balanced first stages are very good at controlling freeze up. Another possible disadvantage of a piston regulator is that ambient water enters the regulator body, along with possible debris and, of course, salt water, which could cause corrosion. And as a result, some first stages are environmentally protected by either creating pressure within the body of the first stage to keep water out, or by surrounding the piston stem and spring with silicone, which transfers the ambient pressure to the backside of the piston. Finally, adjusting the interstage pressure on most piston regulators requires disassembly. This really isn't a big disadvantage because interstage pressure is usually fairly consistent in piston regulators. The advantages of the diaphragm regulators are they're protected, the internal parts are protected from debris and salt because the diaphragm itself keeps the water from entering the internal components of the first stage, and therefore the internal components don't ever see possible debris and salt. Also, the fact that there's lower flow through the orifice means that there's less chance of freeze up. And that would be only in cases where you have extremely cold water. So ice diving or diving in the Arctic, Antarctic. Finally, the interstage pressure is easy to adjust from outside without disassembly in a diaphragm regulator. The disadvantages of the diaphragm are slightly lower flow, which is mainly only an issue at great depths, so most divers will not notice a difference. And secondly, and this is a big disadvantage, is that greater complexity of the diaphragm causes annual service parts to become more expensive, and so the regular service of the regulator is more expensive. Let's talk about maintenance and field service. Prior to a trip, check your regulator hoses to ensure that they're okay. What are we looking for? Cuts, tears, and abrasions in the sheathing and the outside of the hose. In the picture below, the left side hose, the interstage pressure hose, has a torn sheathing. It's separating from the swaged connector, and so we need to get that replaced. Sheathing pulling away from the metal fitting. If you see any separation between the sheathing and the fitting, replace your hose. And third, the hose may be leaking, which is a sign that it's about to fail. So leaking hoses need to be replaced. In the field, First stage leaks can be caused by a number of things. Sometimes the gas may be leaking from the end of the hose, so it looks like it's leaking out of the first stage, but it's really just the end of the hose, which is usually a worn or damaged O-ring. Interstage pressure hoses and high pressure hoses use different size O-rings. Typically, interstage pressure hoses use a 010 or a number 10 O-ring, and the high pressure hose uses a size 011 or 11 O-ring. Keep spare O-rings in your Dive Master kit. Keep a pick in there and some silicone grease so you can easily replace these O-rings if they start leaking. Sometimes those fittings get a little bit loose and the O-ring gets extruded, and then it's no good anymore. It's damaged, so you'll have to replace it. If you have a slight leak coming from the first stage, it could be that the piston head O-ring is leaking, or the diaphragm could be leaking. Don't dive a regulator that's leaking like this. Take it to the shop for service. A major leak from the first stage would be high pressure seat failure, which is very rare, but it can happen, and it's very serious. Do not dive a regulator where you have a heavy leaking gas from the first stage. Take it to the shop for repair. Adjusting interstage pressure. If the interstage pressure is low or high, and the interstage pressure can be adjusted without disassembling the regulator, and the person adjusting the interstage pressure is trained on how to do it and has the correct tools, locate the adjustment. Usually it requires a large screwdriver or a hex wrench. In this regulator, in the picture, it requires a large screwdriver. Depressurize the regulator. If the interstage pressure adjustment is at the top of the regulator, as it is on some balanced piston regulators, turn clockwise to lower the interstage pressure, counterclockwise to raise interstage pressure. If the adjustment is at the bottom of the regulator, as in balanced diaphragm regulators, turn the adjustment clockwise to raise interstage pressure, counterclockwise to lower interstage pressure. Make small adjustments and check to see how the adjustment affects interstage pressure. If interstage pressure is way too high or low, have the regulator serviced. Advanced service on any regulator must be done by trained technicians using the correct tools and parts. During the hands-on portion of this course, we will disassemble and reassemble both piston and diaphragm regulators. This doesn't mean that you will be qualified to work on your regulator or someone else's regulator. And if you want to do that, you can take a regulator service class from one of the manufacturers if you have a relationship with a dive shop. The goal in this course is to diagnose and fix minor issues and to learn more about how regulators function. For more information on advanced service and regulator theory, read Scuba Regulator Savvy by Peter Wolfinger, which is available from a company called Scuba Tools. Scuba Tools makes regulator repair and maintenance tools for the dive industry. Questions? Call me.